Welcome back, everyone. Today we're doing a deep dive into autonomous mobile networks, the ones that manage themselves, and specifically a really clever way to make them smarter.
Yeah, it's fascinating stuff. We're seeing a big push towards these autonomous networks or ANs. The idea is networks that can, say, adjust bandwidth on the fly automatically based on what's needed.
And neural networks are sort of the brains behind this, right? Doing the predictive modeling, spotting patterns.
Exactly. They're becoming central to how these ANs operate.
So, okay, picture this. Every cell tower, maybe every base station, has its own little AI, its own neural network. How do they all learn together without spilling, sensitive user data?
Well, that's where federated learning, or FL, steps in. The research we're looking at uses this technique. Think of it like collaborative training.
Right. The paper mentions federated averaging. So each local network trains its model on its own data,
Mhm.
and then only the changes, the updates to the model weights, get shared and combined, not the raw data itself.
Precisely. That's the beauty of it. Collaborative learning, but keeping the local data private, which is huge.
But there's always a catch, isn't there? These neural network updates, even just the changes, can be pretty big files.
Oh, absolutely. And that's the bottleneck. Mobile networks, well, they don't have unlimited bandwidth, sending huge chunks of data back and forth all the time. It just doesn't scale well.
So that's the core problem they're tackling here. How do you efficiently compress all that neural data for FL in these mobile networks? Make it reliable, make it fast enough?
Yeah, getting that communication piece right is critical.
And the key technologies they explored are tiny language models, TLMs, and this
Ah,
thing called NNCodec.
right, NNCodec. It's actually Fraunhofer's implementation of an ISO standard, the Neural Network Coding Standard, NNC. It's designed specifically for compressing this kind of data.
And they applied this to predict mobile network features, like ping times, signal strength,
Yeah.
sort of thing.
Exactly. Predicting things like ping, SNR, maybe the band frequency being used. They used a real-world data set from Berlin, the V2X data set, to test it all out.
Okay, let's get into these tiny language models first. Language models for cellular data. How does that work? Usually we think of them processing text.
Well, yeah, typically. But the power of these transformer-based models, even small ones, is how they find complex correlations and sequences. They use attention mechanisms, tokenization.
So the idea was, could they treat a stream of network measurements, signal strength, quality metrics, whatever, like a sentence?
Kind of, yeah. Convert the tabular data into strings, then break those strings down into tokens, just like words in a sentence. There's a figure in the paper that shows this concept.
And then the language model learns the grammar of the network data.
That's the hope. They developed a custom tokenizer just for the vocabulary of cellular data and used a really lightweight version of Llama 2, built on something called llama.c, which is known for being efficient.
Lightweight is right. They tested three sizes, 409K parameters, 10 million, and 32 million.
Mm-hmm. Those are the
The
ones.
memory footprint is tiny, like 1.6 megabytes for the smallest, up to maybe 127 megabytes for the biggest. That's minuscule compared to the huge models we usually hear about.
Exactly. These are genuinely tiny in the grand scheme of things, optimized for resource-constrained environments.
And the prediction task was focused on quality metrics: ping, RSSI for signal strength, jitter.
Yep, predicting those output quality features based on a bunch of input features. Things like the MCS being used, transmit power, frequency, GPS info, even site information like maybe traffic conditions or weather. It's all laid out in one of the diagrams.
Okay, so they needed good data for this. Tell us about this Berlin V2X data set. Sounds pretty comprehensive.
It really is. It's high-resolution wireless measurements, all GPS located, collected from vehicles driving around Berlin.
Real-world driving conditions.
Exactly. Up to 4 cars, 17 runs over 3 days, covering about a 17-kilometer route. And they collected a lot of features, 159 different ones.
Wow, what kind of features?
Everything, really. Physical layer stuff, radio resource management details, quality of service metrics, GPS, context like traffic and weather. A really rich picture of the network environment.
But they didn't use all 159 for this specific study.
No, they filtered it. They focused specifically on data points from one operator, Deutsche Telekom in this case, that gave them just over 100,000 relevant data points.
And how did they use that data for the federated learning simulation?
They split it. 10% was held out for testing. The remaining 90% was divided among 5 simulated clients, representing different network areas in Berlin.
Like different environments.
Yeah, residential park, avenue, highway, and tunnel. And the paper even lists how many training samples each client got, which varied quite a bit, reflecting real-world data distribution.
Makes sense. Now back to the tokenization. They needed to turn this numerical network data into tokens for the TLMs.
They used a custom sentence piece tokenizer.
It did, tailored specifically for the language found in the Berlin V2X dataset. And the example they give is pretty straightforward. Something like P-cell RSRQ max equals 77.45 gets broken down.
Yeah, into individual tokens, like P-cell, RSRQ max, then late, then 7445, even spaces sometimes. It's a pretty granular way to represent the data for the model.
So the model is essentially learning to predict the next character or number in this sequence of network parameters.
Pretty much, yeah, predicting the next token in the sequence.
Okay, so we have these 5 TLMs distributed across these different network clients, all learning from local data via federated learning. Now, the communication part, that's where NNCodec becomes essential.
Exactly. This is where the compression happens. NNCodec is the tool they use to shrink those model updates being sent back and forth. It's that open source implementation of the ISO IEC standard, specifically for neural network data.
So how does it actually compress the updates? What's the process?
It's a multi-stage thing. First, parameter reduction. This involves techniques like sparsification or pruning, basically finding less important weights in the neural network update and setting them to 0.
So you just don't send the zeros or represent them efficiently.
Right. It reduces the amount of information you need to represent, then comes quantization.
Reducing the precision.
Exactly. You reduce the number of bits needed for each weight value. This is controlled by a quantization parameter, QP. Higher QP means more compression, but potentially more information loss.
And finally,
It uses an optimized arithmetic coding technique called deep CBAC. This is a form of lossless compression applied to the already reduced and quantized data to squeeze out even more redundancy.
sounds pretty thorough. The standard also mentions a parameter update tree, or PUT. What's that about?
Ah, yes, the PUT. That's a clever part of the NNC standard. It provides a way to reference the changes being made relative to previous updates. So instead of sending the whole update each time, you can send just the differences, the increments.
Oh, okay. So it helps manage the updates over time more efficiently.
Yeah, it adds flexibility. It supports different communication scenarios, like sending only incremental updates, which can save a lot of data, especially if the changes between rounds aren't huge. It also makes the whole thing more robust.
Makes sense. And we've got a figure here showing the trade-off, right? Compression versus performance for different settings.
Yeah, figure 3 in the paper. It shows coding performance for different QP values and sparsity levels for one of the TLM sizes. You can see how increasing compression, like using a higher QP or more sparsity, generally reduces the byte rate.
But potentially impacts the model's accuracy or perplexity. It's a balancing act.
Absolutely. Finding that sweet spot is key maximum compression with minimal, or ideally 0, performance degradation.
So let's get to the results of their experiments. They ran this for 25 FL rounds. First off, how well did the TLMs do before any compression was applied? The baseline performance.
The baseline was actually pretty impressive. They reported over 89% top 1 accuracy for predicting the next token.
For these tiny models, that's quite good.
It is, and the perplexity, which measures how uncertain the model is, was below 1.35. Lower is better there. So it clearly shows these TLMs could learn the complex patterns in the cellular data effectively.
Okay, good starting point. Now, the crucial part. What happened when they turned on NNCodec and started compressing the updates? The paper has this table I with specific runs. Let's look at some highlights where they achieved transparent compression.
Right, transparent meaning negligible performance loss.
Yep.
Okay, so for the smallest TLM, the 409K parameter 1, there's a run listed with a specific learning rate, QP of -26, and 0 sparsity.
Right.
They got the uncompressed data size down from about 424 megabytes to just 12.8 megabytes.
Wow, that's a huge reduction. What's the compression ratio?
Over 97% compression, and the
Yeah.
performance accuracy only dropped by 0.18%, and perplexity barely changed. Basically transparent.
97% data reduction with almost no performance hit. That's fantastic. What about the next size up, the 10M parameter model?
A couple of interesting ones there. One run achieved almost 99.8% compression. Data went from over 10 gigabytes down to about 25 megabytes.
Incredible. And the performance?
Accuracy drop was just 0.33%, perplexity unchanged. Another run for that size used 80% sparsity, so really aggressive pruning.
Okay.
Compression was still high, around 99.3%, data down to about 67 megabytes. And get this, the accuracy actually improved slightly compared to the uncompressed baseline.
Improved. How does that happen?
Well, sometimes compression techniques, especially sparsity, can act as a form of regularization, potentially helping the model generalize slightly better. It's a known effect sometimes.
Fascinating. So compression isn't always detrimental. And the largest TLM, the 32M one.
Similar story. One run hit 99.8% compression, reducing data from nearly 32 gigabytes to under 50 megabytes, with only a 0.34% drop in accuracy.
Cool.
Another run, still over 98% compression, also showed a slight increase in accuracy.
So the overall picture seems incredibly positive. They're demonstrating compression rates well below 1% of the original size,
Yes.
with performance degradation that's negligible and sometimes even a slight improvement.
Exactly. That's the core finding. It shows that combining these TLMs with the NNCodec standard within this FL framework is technically feasible and highly efficient for this kind of mobile network prediction task.
The takeaway really is that this significant reduction in communication overhead is possible without killing the model's performance.
Precisely. Which, has really big implications for actually deploying sophisticated AI in future mobile networks, particularly where bandwidth is a precious commodity.
Absolutely. It opens up possibilities.
It does. And when you see these technical gains, efficient FL, effective neural network coding, it makes you think, what's next? What new architectures or maybe different optimization techniques could push the boundaries even further for these autonomous networks? How much more scalable in real time can we make them?
That's a great question to leave our listeners with. Definitely food for thought. If you want to explore the nitty-gritty technical details, do check out the link to the research paper. Thanks for joining us on this deep dive.
Thanks for having me.
Catch you next time.